Okay, so derivative. Now, normally when you see a tangent line question, that's licensed to pop it into your calculator and go from there. But it's not an explicitly defined function, so you can't just pop it right into your calculator because it's not solved for y in terms of x. All right, so we take the derivative implicitly. The x part of it we treat the same way we treated every other x part of a function. So 2/3 x to the negative 1/3 plus, now I'm going to take the derivative of the y part of it. So it has the same structure, 2/3 y to the negative 1/3. But what else do I have to include? dy dx. So times dy dx.
Wait, are we not having the first one?
We are.
Are we?
Yeah.
Oh, I just thought it's like.
Yeah, no, I didn't get around to writing it. It's like you're only getting around to opening your packet now. So 0 on the right-hand side. Anyway, so constant multiplier of 2/3 across the board. So I can divide out a 2/3. All right. My goal here is to solve for dy dx. All right. Whether you do it now in terms of x and y or later after having subbed in the 81, that's up to you. All right. Life can be easier if you do the substitution earlier on in the process because maybe something that looked intimidating algebraically will turn out to be not that bad. So in this case, if I plug in an 8 for the x, eight to the negative 1/3 is what? 1/2. 1 to any power is 1, so this is going to be 1/2 plus dy dx equals 0. Much easier to solve for dy dx now. dy dx is equal to negative 1/2. That's the slope of the tangent line. We have a coordinate of 8, 1. So if I want the equation of the tangent line, we follow our point slope form. And then pop in the important pieces, the m, the x sub 1, the y sub 1. So we're looking at y equals negative 1/2 x minus 8 plus 1. And that's what the question's asked for, the equation of the tangent line, not just the derivative. All right, so if it said find the slope of the tangent line, we're done at the negative 1/2. But because it's an equation of the tangent line, I need to go with this. Now, if you were actually to plot this line, hopefully it would, or plot it correctly, it will look like it's tangent specifically at A1. But coming up with this graph on your calculator, not the easiest thing in the world, so most people just kind of take it on faith. Now, number 5 is asking for the second derivative. All right, so this is a juicier situation here.
Is the lesson video from yesterday?
Should be.
Oh.
All right, so we have to take the derivative, simplify that, and then take the derivative again. Now, technically, you don't have to simplify it in order to take the derivative a second time, but it's going to be in our best interest to do that. All right, so on the left-hand side, I have two functions. All right, they're being multiplied. All right, so they form a product, therefore product rule. So first function multiplied by the derivative of the second. What is the derivative of y? Just the dy dx. plus the second function, which is y, times the derivative of the first. That's just a clean 2x. On the right-hand side, 1, well, that's constant, so that's going to have a derivative of 0. So the only part that I actually care about is this negative y. The derivative of negative y would be what? Negative dy dx. All right, so I have to solve this for dy dx. All right, I'll clean it up a little bit first. Very little bit. All right, move some things around. I'm going to basically just swap these two guys. All right, just when you swap them, make sure that you give them the opposite signs. All right, I have a common dy dx. Factor it out. And then solve for dy dx. All right, so that's the first derivative. They want the second derivative. So I got to take the derivative of that. So I'm going to rewrite it again up top. All right, we're going to take the derivative of this. It's a quotient. All right, quotient of two expressions. So we're going to use the quotient rule. Left-hand side is our notation for second derivative. Right-hand side, we have to do the low D high, high D low stuff. So this is my low and my high. So low, D high. All right, the D high part, that's going to be interesting. All right, so I'm going to accentuate this a little bit, the product. That negative 2xy is really the same as saying negative 2x times y, right? I'm writing it like that to establish the product that exists within that expression. The reason I'm doing that is to make it hopefully painfully obvious that the product rule should come into play when finding this derivative, right? So embedded in here is its own, quotient rule we have as the overall framework, but embedded in there is some product rule action, all right? So I have a first function and a second function, so I need the first times the derivative of the second. All right, we already talked about y having a derivative of dy dx. Plus the second function, y, times the derivative of the first, which is just a negative 2. All right, so this is my low D high. Now I need the high D low, so minus the high D low. The D low is a little easier to work with, a lot easier to work with, because it's only made up of x terms. So that's just a 2x. And all of this is over the denominator squared. And, you know, if it didn't say simplify, it'd be done here, but the issue is, well, twofold. One, it does say simplify, so we have more work to do. But the other part is, you're looking carefully at our derivative, you see I have x's and y's, but I also have a dy dx. All right, that can go, and we're going to make the change there.
On the left side, I'm just a little confused about the squares, like derivative squared y over.
That's just notation. That's the notation for second derivative.
Okay, but how? So like, why is it after the d?
Because this is the second derivative of the original function y per change in x per change in x. So there's two changes in x, but we're still only looking at the original function.
Okay.
All right, so
quick thing with notation. Would it also be okay to just write f
double prime?
Double prime.
Yes, as long as you don't put of anything. So just the f double prime, that's okay. But if you put like of x, because it's not just of x, it's of y too. If you wanted to do it of something, then do x comma y, because it's in terms of both of them. Okay. So before we get into this dy dx thing, we can clean up around it a little bit. So we might as well do that. All right, so not much, but something. All right, you may consider distributing out a little bit here, but we still have that dy dx. We have to account for that. So something's got to go here. Let's make this yellow, and we'll go with the highlighter. So this has got to go. Oh, that doesn't look like a highlighter. I don't know why it does that. All right, well, whatever. Pretend I highlighted it. I need to replace this guy here. All right, so what is dy dx equivalent to? Negative 2xy over x squared plus 1. We know that because it's written right here. All right, so dy dx is the same as this dy dx, which is the same as negative 2xy over x squared plus 1. So we're going to replace all right, and so we end up with this. All right, a little bit better. I mean, better than it was originally. Not much better than the previous step. In fact, it made it look a little worse. A little distributive property. I can multiply through. I can take this x squared plus 1 and multiply it by this piece, but then also by this piece. Now, this is the one good thing about it. I mean, there's not much good that comes out of this problem, but this in terms of simplifying, this is one thing that ends up being a little bit nice. When you multiply this by this product here, it's going to actually cancel with the x squared plus 1. It won't cancel when you multiply by this one, but what you have as a result of this product multiplied by x squared plus 1 is just going to be the negative 2x multiplied by the negative 2xy. Then after that, you'll have 2y times x squared plus 1 plus 4x squared y.
Don't you have to distribute the x squared plus 1 to the negative 2x?
Since this is a product, these two are grouped together as one term.
Okay, okay.
Okay, so a little bit more cleaning. These two could be multiplied. We could do a little distributive property there. Alright, so we multiply these two, negatives cancel. 2 times 2 is 4, x squared y, so that's giving us this first term. Distributing the negative 2y to the x squared gives us negative 2x x squared y. And then negative 2y times 1, negative 2y, then the rest is as is. We have some like terms that could all be put together. So this one, and this one, right? And what'd you say, 6? Minus 2y over x squared plus 1 squared. And then the final step, at long last, would be when we have a GCF on the top that would be pull out the 2y. And so we're looking at 3x squared minus 1 over x squared plus 1 as a quantity squared. And that would be my second derivative.